In this video, I'll be introducing to you Möbius transformation. So let's get right to it. Okay, so Möbius transformation are also called linear fractional transformations, LFTs, not NFTs, is a function of the form AZ plus B over CZ plus D. So it's a ratio of linear functions. The coefficients A, B, C, D are complex numbers, and it's chosen in such a way that AD minus BC is not equal to 0. So what this condition guarantees is that if AD minus BC is non-zero, then the numerator is not a constant multiple, the denominator. If that happens, then they cancel out and you just get a constant function, which is not interesting. So we're gonna eliminate that case, and all other function of this type forms a group of Möbius transformations. Okay, so Möbius transformation can look like that. So some of these coefficients can be zeros. So if A is 0, you'll get no Z in the numerator. And if C is 0, then you'll get a linear function. Okay. So there's two cases. If the denominator coefficient C, if C is non-zero, then as Z goes to infinity, the function will approach A over C, and A over C makes sense because C is non-zero. If C is equal to 0, then basically you just have a linear function, so that blows up as Z goes to infinity. So what we could do is we're going to define this function at infinity. So we're going to pretend infinity is a number we could just plug in. And you could recompute it as a limit if you like, but we'll write f of infinity to mean either a divided by c if c is non-zero, or infinity if c is equal to 0. Similarly, if the denominator is equal to 0, instead of saying that function is undefined, we'll just set it as infinity. So if the z is equal to negative d over c, then the denominator will cancel out and you'll get 0. And in that case, we're going to set the output of this function to be infinity. So what this allows us to do is to be able to kind of treat infinity just like any other complex number. You can plug it into this Möbius transformation and get an output, or you can plug in certain complex numbers and get infinity as an output. This treating infinity like a number makes sense in the context of Möbius transformation. So we're gonna define what's called the extended complex plane. So we'll just write a regular complex C, Blackboard font C, with hat. And that is complex numbers, all of complex numbers plus infinity as a point that we can kind of plug in. Okay, so that's the extended complex plane. As far as like how you should view this geometrically, if you imagine the complex plane as like a wrapping paper, and maybe like a place like a ball that's sitting on top of the wrapping paper, and you wrap the complex plane around it. So you'll have like a bag that's kind of twisted at the top. You could imagine that twist at the top is the point at infinity, and then you have this ball of complex numbers almost all the way around, and you have one point at the North Pole called infinity. So you should imagine this extended complex plane as a ball or sphere. It's called Riemann sphere. Okay, so we can take the derivative of this guy. So using quotient rule, we get AD minus BC over CZ plus D squared. Notice that AD minus BC appears in the numerator. So as long as this thing is not equal to 0, you have a non-zero derivative. So you have a conformal map. Okay. The condition, yeah, guarantees that f is not constant. Yeah, so I've already said that. Okay. So there's 4 parameters, A, B, C, D. So it looks like there's 4 degrees of freedom, but really there's only 3 because if you multiply each of the constant by same number, let's say K, which could be complex, then you get the exact same mapping. So the coefficient will cancel out at the top and bottom. So there's 1 degree of freedom that's just kind of redundant. But other than that, you have a unique mapping for each of the choices, other than the scaling factor that you might choose. Okay. Möbius transformation is 1-to-1 and onto. From the extended complex plane to the extended complex plane. So to show the proof, we could actually just compute the inverse, right? So if for any output W, we could set the function equal to W, get the denominator multiplied to the right-hand side, and then collect all the z's on the left-hand side, then divide. So we can compute for the input that gives the output W that's desired. So this is the inverse function. Okay. You have to reason out the case where you're plugging in infinity. So you have to worry about that, right? So if C is non-zero, this computation will work. If C is equal to 0, then you have linear function. So when you plug in infinity, you get the infinity out. Okay. So Möbius transformations are conformal mapping from the extended complex plane to itself. Okay, so there's lots of different behaviors that are possible. Namely, when you don't have Z in the denominator, so if C is equal to 0 and you just choose D to be 1, then you have a linear function, right? These are sometimes called affine transformations, which maps infinity to infinity, but it's a conformal map from the complex plane to complex plane itself. Okay, the multiplication A by itself does rotation and dilation, as we know from multiplying by a complex number, right? The modulus will do the dilation, and the argument will rotate the number Z. Okay. If you fix A to be 1 and then change around the B, you get what's called a translation. So you can shift the number Z to the right, left, up, or down, depending on what complex number B is. So that's sometimes called translation. Okay. And then if the denominator c is non-zero, it's a little bit more difficult to see what the mapping does, but let's pick the simplest possible situation there. So we choose c equal to 1 and a0, b1, d0. So 1 over z. This thing is called inversion. So let's try to understand what this function does. So probably the easiest way to see it is to look at the polar coordinates. So 1 over z is going to be 1 over r. So the modulus is the reciprocal. And the argument will be negative. So if e to the I theta is in the denominator, that's the same thing as e to the negative I theta. So argument will reverse orientation, right? So counterclockwise turns into clockwise situation. But this basically means that if you have a circle of large radius, this will get mapped to circles of small radius because the modulus is inverted, and vice versa. So small circles becomes large, and the unit circle will map to unit circle itself. Okay. All right. So what else does it do other than change the radius of the circle? Let's figure out what it does to other circles. Okay, so I chose one circle here. So this is a circle of radius 1, centered at 3. And let's see what would happen, what the inversion does to this circle. Okay, so if I want to see what the output looks like, so let's choose W to be f of that, starting from that circle of radius 1 centered at 3. That's the same thing as looking at 1 over W in that circle, because the inverse of 1 over Z is just 1 over Z. Okay, so that means that 1 over W minus 3, the modulus of that is equal to 1, because that's a condition to be on the circle. And just to kind of get rid of W on the denominator, you could multiply both sides by W squared. So you'll have 1 minus 3W on the left-hand side, and W squared in modulus on the right-hand side. Okay. Here, the next step, I'm going to view this times 1 minus 3 complex conjugate W, because this is equivalent to 1 minus 3W squared. And then if I multiply it out, here's what I get. And then now there's two terms that has modulus W squared. So let's just collect both of those on the left-hand side. And then divide everything by 8. So I'll just get a coefficient of 1 in the leading term. And then I'm going to try to complete the square, right? So I have these two terms. If I add and subtract, or I guess I could add 9 over 64 on both sides. I chose 9 over 64 because that's 3 over 8 squared. Okay. On the left-hand side, this factors nicely. And on the right-hand side, I just have the constant negative 1/8 plus that. So the left-hand side becomes the modulus of W minus 3/8 squared. And the right-hand side becomes 1 over 8 squared. So here's what I got. There's a lot of algebra involved, but basically this means that the output the range, the image of this inversion, starting with that circle, is another circle with different radius different center and different radius. So here's the unit circle. Here's the circle K that we started with. So centered at 3 and radius 1. That mapped to inside of the unit circle with the center now at 3/8 and the radius 1/8. Okay, so everything outside of the circle, unit circle, goes into the unit circle. So that kind of makes sense. But you worked out that the circle transformed into a different circle. Okay, so there are other things that could happen. So let's see what would happen to a different starting circle. Okay, so we're gonna look at a circle of radius 1, centered at 1. So now I'm looking at this circle. All right, so we're gonna go through sort of similar algebra steps, but we're gonna end up with something slightly different here. So I guess I'm not gonna go through each step because they're similar, but the key thing to point out is that at one step, we combine the coefficient of modulus W squared in the previous computation as well. Here we had 9W squared and W squared here, and then we subtracted it and get the coefficient 8. In this setting, it just so happens that they cancel out. So you don't have the W squared term anymore, and what's left is going to be an equation of a line. So the real part of W equals to 1/2. So that's a vertical line that looks like that. Okay, so a circle can map to a different circle, or if it happens that the coefficient of W squared cancels out exactly, then you could get a line. So that's a possibility as well. Another thing that could happen is that if you start with, so because 1/z is inverse of itself, if you started with the real part being equals 1/2, if you started with that line, then it turns into that this circle after the map. So circles can turn into circles, circles can turn into a line, line can turn into a circle, and finally, line can turn into a line as well. So here's an example that looks like that. So if you look at like a diagonal line passing through the origin, 1/z turns into 1/2t minus I 1/2t. If you think of 1/2t as another variable s, this turns into like a diagonal line in the output. Okay. And in this case, when t is equal to infinity, then s is equal to 0. So, so you could think about it that way. So what am I showing here? So what I wanted to show was that this fact. So every Möbius transformation maps circles and lines to circles or lines. So if you start with a circle or a line, you always end up with either circle or line, and every possibility could happen. Or if you kind of think of a line as circle with the infinite radius, or circle that kind of passes through the infinity, then you could kind of think of line as another circle, in which case Möbius transformation maps circles to circles, which might be easier to remember. And if you're imagining the Riemann sphere, so remember we were thinking about the complex plane, extended complex plane with the infinity like a ball, then it turns out that any circle you draw on this ball is going to be transformed into another circle. Okay. All right. So I wanted to offer a different way to think about Möbius transformation. So remember, there's three different kind of parameters, complex parameters you can use to think about this Möbius transformation. So there's A, B, C, D, and one of the constants is a scaling factor. So what you could do is you can choose Z1, Z2, Z3, so any complex number or infinity. So 3 points in the extended complex plane could map to 0, 1, and infinity respectively. So you can pick any 3 points and send those points to this 3 prescribed points. And how do you do that? You could use this formula. So notice, I mean, this doesn't look like a Möbius transformation, but if you look at this factor right here, it involves Z1, Z2, Z3. So these are all constants. So it is a linear function divided by a linear function with a constant sitting in front. So you can just kind of multiply it in into the numerator if you want to write it as a Möbius transformation. And you have a unique Möbius transformation that does that for you. You do have to be slightly careful if you're using infinity as one of those Z1, Z2, Z3 points, and you might get confused. Well, what does Z2 minus infinity mean? What you could do is you could just, every time you get confused with infinity in the Möbius transformation setting, you could just replace it with a limit. So just rewrite infinity as a variable t and let t go to infinity. Take the limit, and that's what you get. Yeah, you have to be a little bit careful with the infinity. But other than that, that's what you get. Okay, there's more. I want to talk about Möbius transformation, but we'll do that in the next video. All right, I'll see you later.